Leonardo Fibonacci, more commonly known as Fibonacci, was born in 1170 in Pisa, Italy. As a child, his father, Guglielmo, a merchant, was made consul of a Pisan merchant community in modern-day Algeria. Thus, Leonardo was sent to study calculations with an Arab master. Later in life, he bounced around the Mediterranean studying numbers and calculation. Interestingly, during his life, Fibonacci wasn't known for the Fibonacci sequence, but rather for his bringing of Hindu-Arabic numerals to Europe, making them more accessible to those other than the intellectual elites. The Fibonacci sequence is what he's known for today, but it wasn't given that name until around 700 years later. It was named after him because in his book, Liber Abaci, he wrote of an observation he made about the mating habits of rabbits. He wanted to know how many pairs of rabbits one pair of rabbits could produce. He reasoned that if you leave 2 baby rabbits in an enclosure and wait a month for them to reproduce, in another month there will be 2 pairs of rabbits, and so on in this fashion. This sequence of reproduction follows the pattern 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on, in which each number is the sum of the previous 2 numbers. In 1634, mathematician Albert Girard determined the formula u subscript n plus 2 equals u subscript n plus 1 plus u subscript n, u being the term and the subscript being the position in the sequence. Then, in 1753, mathematician Robert Simson found that the larger the numbers got, the closer the ratio between them got to the number 1.618, also known as the golden ratio. We can see the Fibonacci sequence by drawing a 1x2 rectangle, then connecting a square to the long side, making a 2x2 square, then repeating this process of adding squares to the long sides of rectangles until we get a shape that looks like this. We can then write a data table of length versus width. You may recognize these numbers as the Fibonacci sequence. We can then plug this data set into Desmos to see what happens. Once we put this data table into Desmos, we can click linear regression, and whoa, look at that slope. 0.618, that's very similar to 1.618, which is the golden ratio. Of course, in the grand scheme of things, these numbers are very small, so it's not going to be exactly the golden ratio. The larger the numbers get, the closer it'll get to 1.618, but we can see the Fibonacci sequence and golden ratio displayed here pretty well. We can see these rectangles as an interesting example of the Fibonacci sequence. If we go back to this picture, we can see that you can draw a cool spiral. Hey, wait, this spiral looks kind of familiar. I know where I've seen this spiral before. The Fibonacci sequence is all over the place out here. Like, look at this flower. And this seashell over here. Even that elephant. Oh, and that hurricane, too. We should go inside. So, as you can see, the Fibonacci sequence appears all over the place in nature. And the interesting thing is, we don't really know why. Scientists have speculated that in plants, especially leaves, it's just an advantageous structure, so it's been passed down through evolution. But it appears in weather, in animals, in the human body, in plants, and it's basically just a coincidence. But we can also see this in mathematics, in this example. We're given an isosceles triangle ABC, where AB equals AC, which equals K. Angle BAC equals 36. And since ABC is an isosceles triangle, we can say that angle ABC equals angle ACB, which means they both equal 72 degrees. Now, if we draw the bisector of angle B to point D on line AC, we can say that angles DBC and ABD both equal 36. So doing some calculations, we can then determine that angle BDC equals 72 degrees and angle BDA equals 108 degrees. Since angle BDC equals angle BCD, we can determine that triangle BDC is isosceles, meaning that segment BD also equals 1. We can use this same logic to prove that triangle ABD is isosceles, since it has a 36 and a 36 degree angle. This means that side AD also equals 1. Now to find the length of segment DC, we can put triangle BDC off to the side to make it easier, where BDC, where angles D and C both equal 72 degrees. We can then create two right triangles, each with an 18-degree angle, and use trig to solve for EC. So we know sine 18 equals 0.309. So then we can say that since BC equals 1, EC over 1 equals 0.309, which means EC equals 0.309. So now we just multiply it by 2 to get side DC. So DC equals 0.618. So now to find the entire thing, we can add 0.618 to 1 to say AC equals 1.618. And my goodness, it's the golden ratio. So from this solution, we can determine that in an isosceles triangle with 36, 72, and 72 degree angles, the ratio of the long side to the short side is going to be 1.618, or the golden ratio.